Yeah, okay, I guess we can start. Okay, yeah, so this will be a joint talk, so I'll do the beginning and Hugo will jump in later, do the actual homotopy groups. And for later, for the next talk, I suggested I give a short presentation about very recent work in progress on finite schemes. So I mentioned it yesterday and people seemed interested. So we can continue with that and move the open problems and the names, which is not a serious suggestion anyway, more to the back of this day. Okay, so A1-homotopy theory is kind of easy to define from an internal perspective because we can just say we have a modality, but I mean, the general concept for nullification modality is a bit scary, so I think it's always good to know that we can at least talk about A1 model or A1 local types without doing anything weird with some crazy high inductive type. So what you can do is just say type X is A1 local, and I mean with that we mean also model later with respect to a modality, but we always say A1 local because it's such an established term also in the subject. So if in a diagram like this, where you can interpret this map as some pair in X, some algebraic pairs, you can always trivialize the pairs. It's just the lifting condition we have already seen a lot. And yeah, that's just the definition. So of, yeah.
Is it equivalent to diagonal map X to A1's equivalence?
Yeah, so another way to say it is this map with an equivalence. Takes elements in X to constant pairs, and this being an equivalence, there are not more than the constant pairs. So every pair is constant, and it's easy to translate between the two. So equivalence you can say as contractible fibers, and this unique existence is exactly this contractibility of the fiber. And yeah, so in general, this means we look at types which are null with respect to this small type family of just one type. And there's a theorem in the modalities paper that this gives you a modality which can universally turn any type into an A1 local type. So we give it a name. So it's called the A1 shape or just shape. The nullification one nullification modality. And this is, so shape is by analogy to Mike Schumann's work, for example, in real cohesion, where you do the same thing with the Dedekind reals. So there you get the usual homotopy types from topology. And what you sometimes want is a truncated version of that, because internally it's hard to see or even false that if you have A1 local types, that truncation preserve this property. So it's a bit more convenient to just have modalities which do both at once, like truncating and taking this shape. So let me also define that. So A1n is nullification at two things. At A1 and Sn plus 1. So the truncation you can define as nullification. So the n truncation is nullification at Sn plus 1, which means if you look at this diagram, you trivialize every sphere above, or at least one above n. But it also means you trivialize everything higher by usual arguments in this direction. And yeah, that's just convenient later for the homotopy groups to have a modality like this. And it's also actually convenient in real cohesion, where you also don't know that truncation is something you can freely apply to homotopy types. Or freely apply with good properties. Okay, so there are a lot of kind of easy examples. My favorite one, I would say, is every I x decidable equality is A1 local. In particular, that tells us that our operation shape is not trivial. Because, I mean, that could be that if you just nullify something, that you collapse everything to the point. We know we at least collapse one thing to the point in the A1. So that's something directly known. So shape A1 is trivial. And this tells us sometimes some non-trivial ones like finite sets or the natural numbers are A1 local. So we know it's non-trivial what to do. So true. That's kind of a base case. First, we look at the map from A1 to blue, or you should think of it as the set 0, 1, and with 0 and 1 being 0 and 1 in our base ring R, and they are different, so we get an embedding, so we can look at A1 to, well, let's put it as tilde, to R. And now we know we have an idempotent polynomial. So I mean, maps like this, as we learned, are polynomials. So we have a P in Rx such that P squared equals P. And it's not a problem doing some x minus 1 to switch 0 and 1. So we can just assume that P of 0 is 0. And you should do it this way. Yesterday night I took 1 and I computed and thought this was easy, but yeah, if you do it like this, you see it immediately. So if you have this, you can, you know, it's divisible by x, so you can write this, and then you get with this equation So you have p prime squared x squared, and x is regular, which means you can cancel it from equations, or multiplication of it is injective. So you get something like this. And then you know all coefficients, like inductively, of p prime must be 0. Because here you shift up the coefficients, and then you can inductively see it's all 0. So that tells us if we have a map like this, it's 0 or 1 everywhere, so it's constant. And this is also interesting beyond like A1 local things. So this is also a notion of connectedness, which is known already in synthetic topology. So, and it behaves very nicely. You also have an operation which makes things connected. It's not a modality, but it's a reflective subgroup stuff. So slightly less. Okay. And if you have this, like the general thing, oops, hard. So we start with a map from A1 to X, and now we can use the decidable equality to decompose X into one point and the rest. So we view it like this. So it's 1 plus, and as a point, we can just arbitrarily take gamma of 0. So we can take all, let's write it as a sigma. So we take all x in x, where x is different from gamma of 0. And from this, we have a map to Boole. And then we can just compose and see this is constant by the above. So we know the map must already be constantly gamma 0. So this is constant. Okay, so we have a lot of examples of A1 local types now. And yeah, what are those things? Yeah, okay. So, I mean, the other extreme is types which are trivialized by the shape operation. So, let's look at it. It's also useful, very useful to have examples in those sometimes. So, say, X A1 connected. Here the terminology comes from the truncation, but it's actually some connectedness. And this means just that the shape is the unit type.
X.
Yes. So, yes. Proof for the examples. So, first of all, I guess it's good to know that infinitesimal things are collapsed. So, D, so the general D, I guess, is the Newtonian R, or equivalent things that are not 0. And yeah, this is trivialized. And then more generally, kind of all concretely within infinitesimal disks. So something you can do in general, I guess it's like this. So we have a case order n-dimensional infinitesimal disk. It's 0 for all indices like this. So all category products are 0. And C all R modules. So all of these types are A1 connected, and it's the same proof for all of them. Like if you have an R module structure and you have one here, you can multiply the invertible elements. Then you can always, or elements from R, sorry, then you can always construct a line. So linear homotopy. Yeah. So you can just do linear homotopy. So this proof that Rn is contractible carries over from topology to this. What is a bit surprising example, maybe, at least for me, it was the universe. This. That's also not hard. So you can just take two arbitrary types, so points in the universe, and you have to build a family over A1, which has this type on one side and this type on the other side, and you can just put them over 0 and 1. And yeah, I forgot what the best way to do it is, but you can just write something down in types. I guess it's universe, then you can kind of take the product with this proposition x equals 0 and co-product with d times x equals 1, I guess. And then you have a family. And I mean, this carries over to a lot of other things. If you have some types, or I mean, it works for a lot of structured types. So I mean, you have here every M in R mod, but you also have the type of R modules that would also work. So they want to connect it.
So can you say a little more, because the shape is a very complex operation. So how do you prove, for instance, that L is A1 connected? Yeah, from module R module. So can you say more? I mean,
yeah. So if you have, so instead of taking two things in the module, we just take one and connect it to 0. So if you have X in M, you define a gamma from A1 to M, where you say gamma of little r is r times x. And now you have something where gamma of 0 is 0, and gamma of 1 is x. And you can use the shape to turn this into an equality. So let's give a name to this operation. So I mean, what do you want to use? You have to use it sigma. Eta x. We use eta. Okay. That's for eta. Okay, what do I have to do exactly? So I can compose with eta, or in this case it's m, to go to shape m. And then I know this one will be constant by construction of the shape. And with this, I see eta of 0 will be eta of x. So I constructed an equality between these two. And now we have to use model dependent elimination to go from this to an actual contraction.
So it's not completely trivial.
Yeah, it's not
how people use modality, it's easy.
And okay, and the same proof works for Pn with the idea of when we have 2 points, you have a third one, which is neither one of the two.
For Pn, no.
I mean, you have, because then you can connect with a.
No, that doesn't help you. No.
Okay.
I mean, there you don't know to which point you connect, so you don't have a contraction center.
Okay.
And so, which is good because it shouldn't be connected for this modality.
Yes. So it's crucial that you have 0 all the time here.
Yeah.
Okay.
And in the argument, you need the shape, you cannot.
Truncation thing.
Truncation.
So I think by this argument you can get that the shape of projective space is path connected.
Yeah.
In the sense that you merely have a path, but you need the truncation because you know that the point is different of one or the other, and to eliminate the or.
You get A1-0 with this notation of the order.
Very good.
Okay. Okay, so what I want to mention next is back to A1 local types and a non-example. So non-example, very important one. So A1 local. Is A times. So this is important because I mean you could suspect that it feels a bit weird that it should be A1 local, but in usual A1-homotopy theory it is, because you have a different setup. So usually you only consider smooth, in the most common version, you only consider smooth things in your site, and maybe it also plays a role that you overfield. I'm not completely sure, but this is usually one of the first examples where you show this one is A1 local, which is surprising because in topology, like you, for example, if you take out 0 in R, you would collapse it to bool, the homotopy type. But algebraic geometry is more rigid, so here you would already get constant maps. So A1 local, so A times A1 local would mean that maps like this are constant and dually, so by duality, this is the same as maps into Rx from Rx and 1 over x. if you say this is constant, then this would mean these are just elements in R which are invertible, but that's not true for our general base ring. So what we get is that we have more maps than the constant ones given by invertible polynomials. So, I mean, what you have here, so units in this ring, or maybe let's just write it just by using like this. So, I mean, what happens is that if you, just to give you some idea of what's going on, if you have an element which is, say, square 0, then you can look at a polynomial like this. And I think if you, so if this is invertible, you have something like this. And I think you have to use this binomial law, and then you should get something like this with the inverse. Let me try it. So this seems this gives 1, and it's the other way around maybe. So I have this times beta, and I have to cancel it with this times this, so it's beta over alpha, and these just cancel because of this, and then
But you have
the unit.
You have the geometric series and epsilon is nilpotent, and then you do not have to do any calculations. So I think this was the exercise in the exercise afternoon.
No, I didn't do the exercises. That happens when you don't do exercises. You have to calculate it. Yeah, okay, so what turns out here is, what do you have? You have, I mean, we mentioned some related result. I guess here you have, no, wait.
Unit plus nilpotent.
Yeah. So I have alpha plus epsilon 1 x1 plus no. And alpha invertible. So,
That's it.
yeah, thank you. Yeah. Okay. Good.
So what you prove now is that we not have that
Yeah,
units up
exactly.
A1 log.
So up to not it works. And that's something we can actually use to figure out what the actual shape of this one is. So, definition. First, A1 tilde is the reduction of our base ring. So, so we have nilpotent elements which are not zero. So we could equally say we kind of identify things which are not equal. And also the equality here will be, so let's say we have a name to this map we get from this quotient map, and just also denote elements like this. Then we have x tilde equals y tilde is the same as x equals y. And we can extend this to A times and just say A times tilde is A1 tilde and taking units in here. And that will commute with taking units. So that's good. And what I'm describing here to you very explicitly is actually a modality, which we have seen yesterday evening in Mike's talk, which turns things universally into something formally entire. So Mike tilde is the modality. Making parts universally formally entire, and that meant so equivalently this is nullification at closed dense proposition, for example. Repeat what we learned yesterday. And from this, we also know it's Lex, so it's a very well-behaved modality. And now we can say what the shape actually is. I guess this deserves to be called a lemma. So shape of A times is A times 11. Yeah, before I do this, maybe some side remarks. I don't know, I'm taking a lot of time, but I guess we can just go on after the first block with homotopy groups. For definition, the type is, and at least once I will call it naively reduced, because it's a definition we haven't used much, and it's a bit naively simple, and we are not sure if you should make it more complicated to actually be the right thing in some sense. So I try to naively reduce if type points, if now for all from X to R such that they are nilpotent. We know that they are not zero. So one direction we kind of have always. So the other direction is always true, because if it's globally not zero, it's pointwise not zero. And in R, that means nilpotent. And now we have pointwise nilpotent. And with this, when X is a scheme, we have this direction. X scheme. Then is it like this? Because with Zariski local choice or some boundedness principle, we can get like a maximum of the exponents we need pointwise and go to global nilpotent. And reducedness is kind of about mediating between those two. And I mean, between nilpotents and not and global and local, or global and pointwise. So if you have remark, so if you have X reduced scheme, you have, for example, that for all functions, pointwise nilpotent or pointwise not zero is the same as globally not zero. And examples, so A1 is reduced. And kind of give a warning here because it's something I proved yesterday night and committed to the repo because it was actually needed in the group to prove that it's following, but we didn't have it anywhere. So warning in progress. So X reduced defined. Then open is reduced. So how can you do it? Supposedly, is you want to prove a not and you have something nilpotent. So nilpotent, and you want to prove a not. So you can.
The F is not the same.
Yeah. Be nilpotent. Then we can look at so G function here. So duality, we can write it as F to the L, say over some little A in A. And there's a problem now. So we know this is nilpotent as a function like this, which means, so maybe let's just write it down. If I have this equals 0, this means there is some k such that k a to the n equals 0. And I would like to use that x is reduced. So if I know a to the n equals 0, I can conclude that a is not 0, and therefore the whole thing is not 0. But I can only do it when f is regular, and when f is not regular, it's nilpotent anyway, any function. So it's not 0 anyway, because it's 0, because this will be empty. So I want to, so I can use the not to make this distinction between regular and nilpotent for f. I mean, under not it will be actually 0. So not much motive, I guess. You can make a case distinction on f regular follows a to the n is 0, and therefore not a is 0, so not g equals 0. F nilpotent follows G and for something. Okay, that's all I wanted to use from reduced schemes. A1-homotopy. Yeah. So we want to know. So first, it's important to note enough is to check. We want to compute the modernization. Here it is. But it's enough to show that our candidate is A1 local. There's a general modality thing because we are in the situation where the fibers of this map, so write it like this from A1. So this is also in the background our candidate map for the map that universally modelizes this one, because and it is A1 connected, which is by the things I erased. Unfortunately, I chose the wrong word. So the fibers here are this D, like, or merely equivalent to that. So they are like merely equivalent to the nil radical to all things that are not zero, which has this module structure, which you can use to contract it. So this is connected fibers for this modality, and then it's enough to show its model. This is a general modality. Or trigger. So we just have to show it's A1 local. So we take some, we take some arbitrary map like this. And what I didn't mention, we also know this map is surjective. So we have a surjection here on, so this pass gamma, on which we can use Zariski local choice. So we have our Zariski cover here and a section here. Good. And what we want to show is that this one is constant. And since we know there are points I can plug in here, it's enough to show it's weakly constant. So enough for all x, y in A1. We want to show gamma of x equals gamma of y. And this is a double negation stable, so we can use double negated propositions, double negation, or a double negated proposition because we are in here. Okay, and yeah, so I'm now in this context where I want to prove this double negated proposition, so I can use finitely many double negated things, and I know I have these lifts over here, so this is sum over some sections Si, which come from an open subset here. And I know they become equal on intersections if I go down here. So I know for all x, not Si of x equals Sj of x. For all x, maybe I should. For all x in Ui intersection Uj. I know this. And this is where I need the reducedness. So I can say I have not just Si equals Sj as functions on the intersection. And I mean, here I have a lot, and now I have arbitrarily many because these indices are from finite sets. So it's good. So I can actually use Sj. Again, because we have a not motive, we can use this, and then we can do them together to get an actual section S, which kind of not exists. And now I can use algebra to get a unit from this. So S is given by some polynomial like this. But because we have a not motive, I can just remove those. 0 because of not. And then I know this map is actually constant and factors this one, so I know gamma is constant. So in this context, where these 2 points picked, I can now show they are equal. Yes.
I have a question about the Stilde and making function for Foley et al. So R should be Foley et al. Of itself, right? Where R et al. So R et al.
You mean the identity map is Foley et al. Yes.
So to me, it reads like that you're then forcing not x is y to be equivalent to x is y, and wouldn't this make nilpotence in R actually equal to 0? Like what goes? Why doesn't it follow?
Yeah, in what situation?
So if the tildification is making things et al. And R is et al. Then
no, R is not it.
Oh yeah, okay, sure. Okay.
Yeah. Yeah, good. And there's another kind of general statement in this direction is so some part of what we used was here that these fibers are A1 connected, and this is actually a more general phenomenon. So remark, if X is a smooth scheme, then X to X tilde is A1 connected, and it's the same argument but using more results, namely that the formal disks, so I mean this D I mentioned is a special case of a formal disk. You have this generally in schemes, and for smooth schemes they are the same as formal disks in some AN always. So they are also A1 connected and get collapsed. So this map is A1 connected, and this means that A1 local types, these will become equivalent. So maps that are mapped to an equivalence by modality are called equivalences for this modality. It's A1 equivalence. But I mean, the part that is unclear in general is if this is A1 local. So there we actually used algebra in between and did some computations to show it. Okay, I guess that's.
Yes, so thank you.
Yeah.
No, and I guess I'll do the second part
After the break, yeah. So,
and maybe you have questions.
yeah.
It's not directly related to what you said. So this forms the Italian replacement. So the path types are given by the dominant, the ordinary.
Not in general, as far as we know. What is the most general thing?
So could you repeat it?
If you want to understand the identity types of the formally Italian replacement type, I thought maybe it's just the domination. So I want to understand beta x equals beta y. So my terms comes in the ordinary.
Yes, so you know that it's the Fermat-Lietal replacement of the identity type because in Fermat-Lietal is a Lex modality, but it's not the same as not in general. So one perhaps the best I could do. So let's say you have a set. Then eta x is equal to eta y if and only if there exists a closed dense proposition that implies that they are equal. I think, which is equivalent to not when the proposition is nice enough. Yeah.
So can I respond to this? Replacement of L, R? Or it's something complicated?
Yeah, I mean, R is the same as A1, so it's just the reductions.
Okay.
Yeah, this works for any smooth scheme. It's just quotient by magnet equality for any smooth scheme.
Yeah, I mean, that's the answer to your question. For smooth schemes, it's not equality.
Also related to that, so in the standard model, which probability topology carves out this probability itself?
Oh yeah, very good question. I haven't thought about that in a while, but I think I never knew it.
So it's maybe something related to the Durham stack, but I don't know anything about it.
Yeah, I mean, this formally-tile replacement is sometimes also called Durham stack or Durham pre-stack in a context where it doesn't behave nicely. Yeah. So risky topos tends to be nice because it preserves covers in the site, but in general, not this, but reduction preserves, and it's related to reduction.
Yeah,
I mean in SDG, so in URS, big stuff, big framework, it arises as a right adjoint to reduction, and there you can see some nice properties, but I think in the Zariski topos it's actually a bit different.
yeah. I think the normal way to do this is to extend your topos to have like infinitesimal extensions or something in rings, and then this is actually part of like a cohesive triple. But I think in the Zariski topos itself,
Over a field, you have a chance that it works, but in general, not so much. I mean, you need that the nil is finitely presented, and there's or finitely generated. It's weird. Yeah.
And have you also proved so that if something is Zariski locally reduced, at least a scheme that is also reduced?
No, that's an exercise.
Yeah, because I think
I suspect this would fail this naively. definition, because you just look at function defined over the whole type, and sometimes you have very little of those. So
Yeah, but when you have an open cover, maybe you can use gluing. So you have
yeah, I mean, this notion is a bit weird for general schemes already. So fine, as you
for a fine scheme, that is a good one, I agree.
But in general, because yeah.
But also for fine, maybe I can mention this question. I mean, there's kind of two ways you could express reduced also for fines. You could ask, given an input and is it not zero? And then another thing you can ask is, does it become zero when you extend scalars to the reduction of R? Which means, given an element which is an input and which is so there's a question in general for a finite percentage R by A. You can ask any element that is spanned by an input and so R. A linear combination with numbers liptons are is not non-zero, but we don't know the colors. Yeah, I mean the meaning of not equal zero in a general kind of standard is a bit clear.
Yeah. So yeah, there are a lot of unanswered questions about reducedness. So it's why I want to emphasize naive. One naive definition which helps in this case, but I have doubts it's the right thing to say in general.
Yeah. Yeah, just a remark, slightly less naive is to, rather than function, consider closed subset. And then you get something like a type X is reduced if for any closed dense, you have not the closed dense is equal to the whole set. Which at least interact with Zariski cover in a pleasant way.
Right, that's something we, I think, also propose. I don't know if we have a collection of all the proposals for reduced.
I think so.
We should have.
Yeah.
Yeah.
Okay. Thank you.